Hello makers. Today we're going to start assembling our weather station, starting with a closer look at the final wind direction and speed sensor design, as well as working on the housing for the BME 280 combination temperature, humidity, and barometric pressure sensor. So let's talk about the radiation shield that will house the BME 280 sensor that reads temperature, humidity, and barometric pressure. So we've started off printing in ASA directly, and I should mention this is a design that's available on Thingiverse from Thingiverse user Micromet. So we're just downloading that, and we're going to use this as is. We may have to print a few parts to get this sensor to fit in here, but by and large, this is as available online. So ASA is a higher temperature thermoplastic that's designed to be resistant to UV radiation and the high temperatures of the sun. So basically this will warm up a lot more before it begins to deform. Now, ASA is something that I haven't printed with before, so typically when you use a new filament chemistry that you're unfamiliar with, you start off with the manufacturer's recommended settings and you print what's called a temperature tower for calibration. So these are essentially a tiered model, and as you change tiers, you increase the temperature or decrease the temperature, and you hold all other 3D print variables constant. So print speed, layer settings, everything else is just, you leave that set, you change the temperature only. Then once you iterate through the process and you find something that looks fairly decent, then you can begin to fine tune that. So essentially we started here using the manufacturer's settings in our Raise 3D printer, which has an enclosure into it. ASA loves to have a slow, even cool down period, otherwise it begins to warp fairly significantly, probably more so than any other filament I've worked with, be it PLA or ABS. So we started here, and this is 30 millimeters per second with no cooling, and it just didn't print right at all. A lot of deformation in the features here, so not so good. So the next option was, again, 30 millimeters per second, but in this case we took the lid off of the enclosure. This is with the lid on, no cooling. This is with the lid off, and we can see we got a little bit better definition here in the wedge side. So then the next one was printed with the cooling fan turned on, which is somewhat counterintuitive to the manufacturer's recommendations to not use cooling. With the heated build chamber, the interior temperature is probably closer to about 100 degrees, so you get that nice even cool down. So the part wants to be cooled in certain features to get them to solidify quickly, but then the rest of them cool down slowly. So we did that one at 30 millimeters per second, and then the next one was done at 50 millimeters per second. So I was trying to get a little bit faster print time to save time in the long run. And with the temperature tower, there wasn't much difference in the two speeds. It was very difficult to kind of make that determination. So we started printing ASA at 50 millimeters per second, and it was just giving us a lot of problems here. This is an example part here, and you can see there's a lot of warping and over extrusion, and just didn't come out very well. So ultimately, in the end, we had to slow down our ASA to print at 30 millimeters per second, which is what these here are printed in. So we have, let's see here, 2, 4, 6 of these. And then we have a bottom piece here. So we'll need to print something here that will accept the BME 280, which is a pretty small sensor. So if we take a look at this, guys, really only a few centimeters by a few centimeters. So we'll need to print a carrier for that, and then that carrier will get installed here. There are a few other elements here we need to worry about. How we mount this to the support arm, so there will be a piece that goes underneath here. So we're still a little bit work in progress with this, but we're printing it in the high temperature plastic. This way we're ready to go with deployment. Alright, so let's go ahead and start putting together the wind speed sensor. And what I started with was a design by B.H. Martin on Thingiverse. And his design was for an anemometer that was a visual indication of wind only. So he had 3 cups here, the central hub, and the cover for it. And it would just spin around when the wind blew. So there was no instrumentation for recording that electronically. But I liked his anemometer design so much that I wanted to start with that as the core. So this was his original hub design, and trying to figure out how to translate that down to a sensor. I printed this adapter, which let this fit in here like that. So then I could prototype this with the rest of the hardware here. This is the bearing sleeve. So we've got a 608 bearing up top here and one on the bottom. And then we just come back down to here like this, and that gives us our rotational axis. There's just a lot of friction here still. So while this initial design worked pretty well, we came up with something a little bit better for the final design. So let's take a look at that. So here we have a slot for a thrust bearing. So essentially a thrust bearing works when the load is vertical, and we have our balls here and the track in which they ride in, and it fits like that. So a little bit different from your standard radial bearing. So the radial bearing works generally in this orientation with the load going down this way. So your axis of rotation's here, load goes down that way, and the balls rotate in a circular track as such. So thrust bearing designed for to be used in orientation like this. So this will give us a much smoother rotation. So let's go ahead and start putting this together. So we'll start here with our hub, and we'll go ahead and fit in one of the bottom washers for the thrust bearing. And then let's go ahead and place in the wind cups. And one of the other things I really liked about B.H. Martin's design is kind of how these are all keyed in here. So they kind of fit in like this and lock into place with the hub on top. And I just thought that was really clever and kind of a nice design that lends itself well to 3D printing. So this is all made out of PLA. So this is a proof of concept piece. This guy printed out a little bit of a problem there, but when we go to deploy this, we'll reprint this using ASA, which is UV resistant, and it's a much higher temperature plastic, so it should withstand the intense summer sun that we get here. So let's go ahead and secure that in with some bolts. And again, these were kind of junk box find parts here. Come from an old 3D printer, and it just so happened to fit this just right. Of course, now I need to get these lined up properly. There we go. And we get these snugged in here, and that'll be the top piece. Then we can talk about the sensor body. So as I said before, this was just a visual indication of wind. So you'd put this outside, and you'd look, and you'd see it, moving along, and you know there was a light breeze. But how do we turn that motion into an electrical signal that we can then do something with? And that's where our sensor body is going to come into play. And the original intention, and it still is to use the same magnetic rotational sensor in the wind direction sensor as we do the wind speed. So we have a single sensor, 2 sensors. That means we need a common sensor body to go off of. So here's our finished top piece. We'll put that aside. And we have here the bearing sleeve. So essentially, we needed some additional length here for the shaft to be held so we get secure in this direction here. And there was a second Thingiverse design. Let me see if we can find out who that it needs to be credited to. Da, da, da. Yeah, so Thingiverse user Femoral had also come up with a anemometer design, and his had two bearings, shaft going this way, and then the sensor was at the bottom, so you get your rotational movement here. Um, but it was two halves that got glued together. So I wanted to kind of borrow that idea and kind of make it into something that we can just thread on. So this is our sensor body here, and we have threads here and threads here in the top of the bearing sleeve. So this would be assembled as such, and we have our shaft here, and this goes in. And we need our thrust bearing washer here. There's our thrust bearing. And so then we'll have a magnet on the end here. So the AS5600 is going to sense a rotating magnetic field around the top of this chip. So we'll have a magnet on the end of this, and that'll rotate around as this spins, and the sensor will then convert that rotation into an electrical signal that we can then quantify later and derive useful information from. And so the way this works is we'll wire this up, we'll have wires fed into the bottom there, and that fits in there just like that. So then this will sit on the support pole, and all we have to do is come up, drop this in, and thread this onto the top. And we can see here that the shaft is actually making contact with the top of the sensor. So what we'll do is we'll make some adjustments for size here. Oh, come back here. And all we have to do is kind of push this into here a little bit further. And now that's free floating above the sensor. And we'll make some adjustments to get that magnet holder right where it needs to be, but that'll be for a little bit later on. But right now we can see we've got good smooth rotation, and I think this is going to work just great. So after the wind speed sensor, the wind direction sensor was a lot easier to come up with. Rather than adapt an existing design out there, I decided to go ahead and create our own. And what I came up with was a simple dome-shaped hub, and we reused some of the 8mm aluminum shaft and 3D printed the tail fin and the nose cone. Now, the only real big design consideration with this type of sensor is that you do want to have balance across the rotational axis here. So don't want to have this side be too heavy or this side be too heavy. Otherwise, it won't accurately portray wind direction. So there are some bearings here, and we can kind of see them here. And they're just glued into place, and they act as a counterweight there. So um, that works out nicely. And these are hot glued into place. Unfortunately, some of the fitment wasn't the best when I printed this out. So this one comes apart, but the nose cone was sliding too freely up and down here. So I had to glue that in place with a little bit of hot glue, as well as the tail fin here. But again, these are draft components to do proof of concept work with. So overall, really pleased with how this turned out. And again, we're using the thrust bearing here on the bottom side to give us smooth rotation, and the interior is identical to our wind speed sensor. So really happy with how this came out. Interestingly, 3D printing is an iterative process. So as we go through the design phase, looking for something that fits perfectly, I had to go through about 5 iterations to kind of get this nose cone just where I wanted it. And even then, still need a little bit of glue to hold those in. But overall, the wind direction sensor functions nicely, and we're looking forward to getting this wired up and getting some data from it. Now that most of the mechanical design and construction is started, let's take a look at the programming aspect of this. Originally, we had chosen Home Assistant to be our user interface. This is our front end. And ESPHome as a plugin for Home Assistant that manages the ESP8266 wireless chips and is based on the Arduino platform. So many of the libraries and code that you've written for Arduino, you can bring over here without issue. There are some creature comforts that kind of make this a little bit easier for managing multiple wireless devices and configuring them. So let's kind of take a look at some of the code that's going to be used to do proof of concept and get our sensors talking to Home Assistant. In Home Assistant, they use YAML, yet another markup language, to do the configuration files. So this looks a lot different than Arduino C++, but we can see some commonalities to it. And originally I had hoped to use a vast majority of this interface in getting all the sensors to work together, but I ran into a few roadblocks and I kind of want to just go over those briefly here so we get an idea of where this is useful and where we have to fall back to doing some traditional coding. So first off, most of this is going to be provided by the system automatically as part of a template. So, I've chosen the Node MCU as my processor. They've got some logging and API access. Since this does over-the-air updates, there's an OTA password. Of course, we got our Wi-Fi settings here, so the system connect to our network. And then here's where we start defining the features that we want to have in here. The first of which is to use an I2C bus, and we define our pins that are for data and a frequency. And then here we have an entry for our I2C multiplexer, so the TCA 9548A, that's our 1 to 8 port multiplexer. And essentially the reason why I needed this is that the AS5600 has an address hard-coded from the manufacturer, so we can't change the address of that chip. So if you want to use more than two of them in the same project, you have to use a multiplexer to break that bus into multiple segments, so you can have devices with the same address on it. So that was kind of the first roadblock into getting two of the rotational sensors to work together. We have our BME 280 temperature, pressure, and humidity sensor. So this is built into Home Assistant. So there's already a platform for this. So all I have to do is say, hey, I'm using the BME 280. I say it's going to be on one of the multiplexer channels. And really, Home Assistant does the rest. This is all example code taken from the BME 280 example file. So this is default. So nothing changed here, and we can just use this as is, which is why I wanted to use ESPHome, is because we can kind of configure all of these sensors without having to write complex code, and it takes care of all the data collection for us and databasing. So real handy to use. So the next part is to define a custom sensor for the rotational sensor, the AS5600. And again, this is just following the how do I create a custom component tutorial in the ESPHome documentation. I've even left the default my custom sensor, and in fact the units of measurement here even need to be changed to something else because they had used a pressure sensor as the example. But the point being is that we want to use as much of the example code that we know works. So once we kind of get it reporting some piece of information, we know that okay, data is going from A to B, and then we can start making some adjustments to fit our specific use case. So essentially, once we have this here, we need to go back and look at the My Custom Sensor code itself. So this would be written in C and would be very similar to what you'd see in Arduino. So let's go ahead and take a look at that. So here we have the Studio Code Server plugin for Home Assistant. So this breaks out our header files and our code files in a way that we would be accustomed to using an IDE environment. So we get colored coding of what they are, and we get access to the API here. So very, very convenient plugin to have. And this is the custom sensor file that deals with um, talking to the 5600 series chip. So we have our include files, which you would see in an Arduino, and we have essentially a setup, just like we would in Arduino, and as well as a loop, which in this case is called update. And again, this is all taken from the tutorial on how to create a custom sensor. The only bit of code that I added was the library files that we need to make our sensor run, and the bit of code that initializes the object, and then finally a piece here that gets some information. In this case, gets the raw angle from the sensor and then publishes that value. Once I can verify that this works correctly, then we know that, again, A to B is working, and then we can go into more detail as to the math that's involved in taking this raw angle and converting that into an actual either wind direction or wind speed. And we'll talk about instrument calibration in following videos as we get the construction finished and we start getting the wiring in place. So this is our test setup for the dual AS5600 rotational sensors. So we'll say, for example, this is going to represent our wind speed sensor, and this one's going to represent our wind direction sensor. This chip here is our I2C multiplexer. So this is a TCA 9548A. So this is one channel in, 8 channels out. And since each one of these sensors has an identical address, we need to make use of this multiplexer in order to get both of these to function on the same I2C bus. And then this is our ESP8266. This is the Node MCU format. So breadboard friendly, plugs in via USB, onboard voltage regulator. So pretty convenient as development boards come. And the configuration we have here is we have our primary I2C bus goes to our multiplexer, and then on channel 0 we have first AS5600, and on channel 1 we have the second AS5600. So I've installed the basic Arduino code, and we verified that both of these sensors are reading and responding correctly using the multiplexer. So we know that this configuration is going to work, and we can use the same identical sensor for both of our wind speed and direction as originally planned. And finally, for the magnetic sensor, the rotational sensor, we have a little cap here that goes on the end of the shaft, and the magnet sits right in there. That's press fit into place. So this will be the magnet that rotates that the sensor then detects. Thank you for spending time with us today, and I hope you'll join us again next time as we continue our journey. If you have any questions about this project or would like to know more about Exploration Commons, please don't hesitate to reach out. Thank you again, and take care.